Um, some of you may have seen a few of the ideas that we've covered in this class so far, and maybe you've seen quite a few of them. For all of you, if you're planning to take the college level math classes, none of this time is wasted at all. Okay, I can tell you if you're spending time figuring this stuff out, working hard to get a good grade in this class and understand the material here, your life is just going to be that much easier when you see this material again in a college level course. And you can get a nice solid A on a college transcript, improve your GPA and all that sort of stuff. So it's well worth putting the effort in. Okay, so just keep that in mind. We're going to, in 2.6, we're going to cover something called rational functions. This is going to take today and tomorrow pretty easily to cover. Lots of what seem like very strange ideas, perhaps, if you haven't seen these before. But hopefully by the time we get done with this, we'll make it relatively easy to understand. It seems like a long process. We'll make it as short as we can and make it as understandable as we can, and also help understand why these functions make the shapes they do, because these by far are the weirdest type of graphs that you're going to see, at least for quite a while. Okay, so the starter question here says, which fractions are proper and which are improper? So is this a proper fraction or an improper fraction? It's proper. Okay, this is proper. What makes it proper? Now, there's a difference between proper and reduced. This is not a reduced fraction, but it's still proper. What makes it proper? Hop? The numerator is smaller than the denominator. That's what makes it proper. Now, we still reduce this. We'd still write this as 1/2. Okay? And even that, the numerator is smaller than the denominator. Okay? So that is a proper fraction. Proper or improper here? Okay, this is improper. Okay? Now, the numerator is bigger than the denominator. Normally, we'd take this and we'd write this as 2 1/6 in like a pre-algebra class, or if we were in 7th grade or something like that. Okay. Once you get to algebra, we normally leave these improper fractions as improper fractions. You don't write it as a mixed number. Okay. So this one right here was proper. This one is improper, but we're going to leave that alone. Okay. If I take a look at this one right here, example C, is that proper or improper? Okay, it is improper, okay? But this type of improper is a little bit different than this type of improper, and you can kind of tell. This one clearly is, the numerator is larger than the denominator. Here they're exactly the same. So not only is it an improper, but it's kind of a nice type of improper because we could easily simplify this and end up with an answer of 1. So the top is exactly the same as the bottom. Okay, so it's kind of a nice category of improper. Okay, so keep that in mind. That idea is going to come up again. Okay, and then it says state the degree of each polynomial. What's the degree of this polynomial right here? It's degree 3. Again, it's all according to just the leading term. Okay, once you write it in descending order. What's the degree here? Degree 1. And what's the degree here? Degree 0. Now, we could indicate this very easily. You can see that the highest power is 3. We could write that the highest power is 1, and if we had to put something on here, we'd put x to the 0 power on there, and that's why that's a degree 0 term there. Okay, any questions there? Okay, so let's talk about this little paragraph that we've got right here, and let's talk about what the root word of rational is. What is the root word of rational? Ratio, okay? And we talked about this before when we were talking about rational numbers. So a rational or a ratio is a fraction, okay? In other words, it is a division problem. Okay, if you've got a fraction, you've got a division problem. Okay, and that's what we're dealing with today, is we're going to deal with functions that have division in them, okay? And it's a specific type, okay? And we're going to be graphing rational functions, and in order to do that, we're going to have to remember a lot of different things, like basic graphing skills, how to find the domain of a function. We're going to be doing a bunch of factoring, so that's not going to go away, and I mentioned that when we reviewed that in the prerequisite chapter. We're going to talk about simplifying rational expressions, okay, and a bunch of other algebra and graphing skills, okay? So there's really a whole bunch to remember and keep track of here, all right? Now, in order to go through graphing a rational function, you kind of have to do it in a systematic way. Now, every textbook and every person kind of tweaks this just a little bit, but we're going to go through a basic technique. But what's really important is you're going to need to think about the information and put it all together. So sometimes you're going to have to pause and say, well, what does this piece of information tell me about the graph? Tells me maybe where it crosses the x-axis. Tells me, well, I don't have any points right here, or something like that. Okay, so let's talk about what a rational function is. A rational function looks like this. Okay, now I used a capital R of x to represent that we're talking about a rational, and then I've got a P of x and a Q of x. And both P and Q are polynomials. So it's basically a fraction that has a polynomial on the top and a polynomial on the bottom, but I've got to be a little bit careful. Okay, whatever's on the bottom, it cannot be the zero polynomial. Okay, I can't have a zero in the denominator. So this brings to light the first issue when we're dealing with a fraction like this, with a rational function, and that is the domain. Okay, the domain for a rational function is all real numbers. Normally you can plug in anything you want except what will make the denominator equal to 0. Okay, and again, why can't the denominator, why can't this q on the bottom, why can't it be equal to 0? Because it's division, right? And then we'd be dividing by 0. Okay, so we're going to look at the most basic rational function to start off with. Okay, and we're not going to do a bunch of XY tables for the most part, but we are going to do one on this one right here. Okay, so this is called the reciprocal function, and it is a rational function. I've got a polynomial of degree 0 on the top, and I've got a polynomial of degree 1 on the bottom. Okay? Now, let's talk about domain for just a second. Is there a number that we cannot plug into this? Can't plug in a 0. Okay? So x cannot equal 0. Any other number is okay. So I'm going to make an XY table, and we're going to pick some numbers to plug in. Now, let's plug in some fairly easy positive ones to start off with. So if I plug in a 1, I get 1 over 1, which is 1. So I have a point on the graph right here. 1, 1 is on the graph. And I'm going to go ahead and I'm going to label that, because that tends to be an important point. Then let's plug in a 2. If you plug in a 2, what do you get? You get 1 over 2. You get 1/2. What if you plug in a 3? You get 1 over 3. In fact, no matter what number you plug in, it's always 1 over that number. So what happens is I plug in larger and larger numbers. What happens to the function values? They get smaller and smaller and smaller. So I got a 1/2, then a 1/3, then a 1/4. If I went out to 100, what would the function value be? 100th. If I went out to 1,000,000, 1,000,000th. So it gets smaller and smaller and smaller here. Okay? So it does something like this. Now, does it ever actually equal 0? And does it ever equal a negative? Nope. So it stays positive over here. So I'm going to just draw a line like that. Okay? Now, let's plug in some more interesting points. I want to know what happens in between 0 and positive 1. So let's say I plug in a positive 1/2. If I plug in a positive 1/2, I get 1 over 1/2. This has a name, remember it. It's a complex fraction. Flip the bottom over and multiply. What's 1 over 1/2? It's 2. So if I plug in a 1/2, I get out a 2. What happens if I plug in a 1/3? 1 over 1/3, flip that over and multiply, so I end up with a 3. In fact, if I plugged in a 100th, what number would come out? 100. Okay? So this is what the reciprocal function does. When you plug in really big numbers, it makes them really small. It flips them over. The reciprocal of a really big positive number is a really small positive number. And when I do the reciprocal of a really small positive number, so if I plug in numbers like a 1/2 and a 1/10 and 100th, it flips those over and I get very large values out. So imagine if I could go to 100th on the x-axis, I'd have to go up to 100. So what's happening over here is the graph has made a big bend and then it pretty much goes almost straight up and down. Okay? In fact, let me make this look a little bit better, more like a curve. So it's going to go like this. Hit these points, bend around, and go like that. Okay? Any questions? Okay. Well, what happens if I plug in negative values? So I'll make another little XY table. Let's say I plug in -1. What do I get? 1 over negative 1, negative 1. Okay? So I'm going to put that point right here. And if I plug in a negative 2, negative 1/2, right? Well, let's talk about what happens here. As I plug in larger and larger negative numbers, the reciprocal of a large negative number is a small negative number. Okay? So it does something like this. Now, does it ever actually reach 0? Nope, that's not going to equal 0. Okay? And it's always negative because it's a positive on the top, and we're plugging in a negative on the bottom, so I've got a positive over a negative. It's always going to be negative. Now, what happens if I plug in a small fraction in between negative 1 and 0? What's the reciprocal of negative 1/2? Negative 2. Okay? So the same type of thing happens. When I plug in small negative numbers, their reciprocal is large negative numbers, so I get a shape that looks something like this. So it's very symmetric. In fact, we could say this has a certain type of symmetry. Does anybody know what we'd call this function? It's odd because it's symmetric with the origin. Okay? All right, any questions? Okay, that's about the most basic rational function you can have. What would happen if I had that same function and I added 1 to it? What would happen to this graph? What would it do? Shift it up 1. Okay, it would move that exact same shape up 1 unit. Okay, so now we want to talk about some important features on this graph. Raise your hand if you've heard of the word asymptote. Almost everybody? Okay, good. All right, so let's talk about what an asymptote is. Because most rational functions have an asymptote, and this is how you spell asymptote, and you don't say asymptote, okay, or anything weird like that. It's asymptote, okay? Kind of a very silent P there. Okay, an asymptote is a line or a curve, it can be a curve, that approximates the graph. Okay, and here's what asymptotes do. Asymptotes help us get the shape of the graph right. And most of the time, we're going to have things that are like vertical asymptotes. Okay, a vertical line that the graph approaches from either the left or the right. So if we were to take a look at this graph that we did right here, it has a vertical asymptote. That vertical asymptote is right here. Because what happens as we approach 0 from the right side is it goes up, okay? It approaches that vertical line. It gets really, really steep like that vertical line. And as we approach 0 from the left, it gets really, really steep because it tends toward negative infinity. It tends way down there, okay? It's going to decrease without bound is what we call that, okay? And then a horizontal asymptote, which we would kind of abbreviate with an HA, is a horizontal line that the graph approaches at either the right or the left endpoints on the graph. So when we say the ends, what we're talking about is out near the right end, near positive infinity, or out near the left end, near negative infinity. And this also has a horizontal asymptote, okay? So the vertical asymptote is x equals 0, and the horizontal asymptote, which I'll label HA, okay, is y equals 0, okay? So if I were to look at this graph right here, 1 over x plus 1. What did we say this would do to that graph right there? It would move it up 1. Well, if it moves everything up 1, will it change the vertical asymptote? Not the vertical asymptote, okay? Because the vertical asymptote is right here. It's x equals a number. We're changing y coordinates. We're bumping everything up in the y direction. So what would happen on this is we'd have the same vertical asymptote. What would the new horizontal asymptote be? If we bumped everything up 1. It would be y equals 1. Okay? And the graph would look something like this. Okay? Any questions there? Okay. So that's about the most basic rational function that we can have. And now we're going to talk about some other ways that we can figure out, if I've got something more complicated, how can I figure out what this rational function looks like? So the first thing that we're going to talk about are those two words, proper or improper. And we can actually apply these to fractions that actually have polynomials on the top and bottom. So a proper fraction is one where the degree of the numerator is lower than the degree of the denominator. Kind of makes sense. Top is lower than the bottom. Okay, and an improper rational function is where the degree of the numerator is equal to or greater. Oops. Greater than the degree of the denominator. Okay? So, take a look at this one right here. I've got several examples, and we're going to use these examples in quite a few of these. They'll change just slightly from problem to problem, but we'll do a lot of the same things. Is this proper or improper? I see some people mouthing it. What is it? This is proper. Okay? The reason it's improper is that's degree 1 and that's degree 2. Is this proper or improper? This is improper. Okay? That's degree 2 and that's degree 2. So it's equal to on the top and bottom. And is this one proper or improper? This one is improper because that's degree 2 and that's only degree 1. So clearly that one's improper. The top's a greater degree than the denominator. Any questions there? Okay. Well, here's why we talk about proper and improper with rational functions. Okay? We use them to help us figure out whether or not we've got a horizontal asymptote or what we call an oblique asymptote. Okay? An oblique also can be called a slanted asymptote. So the word oblique means slanted. Okay? Kind of on an angle. So you only need to write one thing down in this little box right here. I'll tell you what it is in just a second, so you can just listen to the explanation. Here's why we talk about proper and improper. Okay? If the rational function is proper, you can stop right there and you can tell what the horizontal asymptote is. Immediately, you know the horizontal asymptote is y equals 0. So you know you can draw a long dotted line right on the x-axis. That's the horizontal asymptote. Okay? It's just like this horizontal asymptote right there. Okay? So if it's proper, you can stop right there and say, I know what the horizontal asymptote is just by looking at it. Okay? It's got to be y equals 0. Now, if it's improper, we've got two categories here. And this is my own informal mathematical language. You've got the good type of improper and the bad type of improper. So the good type of improper is good because it's very easy to deal with. And it's easy to tell that it's the good type of improper. Okay? The degree of the top is the exact same as the degree of the bottom. Okay? So numerator and denominator have the same degree. So that's this type right here. This is the good type of improper. Okay? And the reason we like that type of improper is because the horizontal asymptote is still very easy to find. It's y equals the leading coefficient of the top over the leading coefficient of the bottom. So we're used to using that leading coefficient to tell a lot about the shape of a graph. Same thing is true here. Make sure it's in descending order. Okay? Grab the leading coefficient on the top, put it over the leading coefficient on the bottom. That's going to be our horizontal asymptote. Okay? Now, if it's the bad type of improper, and here's why it's the bad type. These both are relatively simple to deal with. If it's the bad type of improper, that means that the degree of the numerator is higher than the degree of the denominator. Okay? In this case, if you want to find what the asymptote is, you've got to do long division. And the answer is y equals the quotient. So here are our choices. If it's proper, it's y equals 0. If it's improper but the good type, it's y equals the leading coefficient over the leading coefficient, which is relatively easy to do. I'll show you how to do that in a second. If it's the bad type of improper, then it's going to be y equals the quotient of a long division problem. And we all love long division, but it still takes a while. That's why they call it long division, right? Okay, now most of the time this produces a slanted asymptote. Okay? So the bad type of improper is harder to deal with, but by the time we're done with this tomorrow, you'll see that actually slanted asymptotes aren't that bad. And they're actually pretty nice to work with because the logic of working with a slanted asymptote is a little bit easier than the other ones. Okay? So I'm going to leave this right here. And it says, does the graph for example 1 fit the description above for proper and improper? Now, for proper, what's the horizontal asymptote if it's proper? Y equals 0. Let's slide back up here. You don't need to flip the page over. Look at this right here. Is it proper or improper? What's the degree of the top? 0. Degree of the top is 0. What's the degree of the bottom? 1. So because the top is lower than the bottom, it's proper. So that would be y equals 0. Did we have y equals 0 for a horizontal asymptote? We figured that out by plugging points in, right? Any questions? Okay, so you have some problems that are literally this easy, or portions of your problem are literally this easy. It just says find the horizontal or the oblique asymptote. It comes down to this. Is it proper or is it improper? So let's take a look at this one right here. Proper or improper? Proper. Okay? What that means is y equals 0 is our horizontal asymptote. That's it. Done. End of story. That is the horizontal asymptote. Pretty easy. Let's look at this one. Proper or improper? Okay, this is improper. If the answer is improper, then you have to ask yourself, is it the good type or the bad type? And which is it here? This is the good type. If it's the good type, then here's what we get. We get y equals leading coefficient on the top over the leading coefficient on the bottom. What's the leading coefficient on the top? 2. Leading coefficient on the bottom. Leading coefficient is 1. You with me? So it's 2 over 1. So y equals 2 is our horizontal asymptote. Okay? Any questions? Okay, you don't need to write this down, but I do want you to watch. Everybody watch, please. The key to solving these and graphing rational functions is to put the pieces together. This is a huge chunk to find out what the horizontal asymptote is. This is what we know about our graph. It's got a horizontal asymptote here. So out near the end, it's got to get really close to the x-axis, either from the top or from the bottom. Same thing over here. It's got to get really close to it, either from the bottom or the top. Okay? If I know that the horizontal asymptote is y equals 2, here's what I know. It gets really close to this line out near the end. So it's either got to come up here and get close to that line or come down here and get close to that line. It doesn't run along the x-axis like this one here does. Okay? All right, so let's take a look at this last one. Proper or improper? Improper. Good or bad? Bad. Because the numerator is degree 2, the bottom is degree 1. If that's the case, then I've got to do long division. Now, you could do synthetic division on this one. I wouldn't if I were you. It's just as easy to do long division, and you're going to need the quotient written as a polynomial anyway. So here's what we're going to do. I'm going to do x plus 2 outside the box. Make sure all the powers are represented and that it's in descending order. I need an x. That's x squared plus 2x. Oops, I normally don't write that. Change the signs. That's a negative x. That's a minus 3. What do I multiply x by to make it a negative x? A negative 1. Multiply here. That's a negative x. That's a negative 2. Change the signs. So the remainder is negative 1. Now, do I care that the remainder is 1? Let's go back up here and look. If it's the bad type of improper, it's just y equals the quotient. Where is the quotient on this? Right there. Okay? So y equals x minus 1 is the slanted asymptote. Okay? So I'll call that SA. And that's it. If you're asked to find the slanted asymptote or the oblique asymptote, that's what it is. So what that means is, if we were to graph this, here's our asymptote. This is in the end. If you were to zoom out and look at what it looks like out on the ends, it looks like that line right there. So over here, it's going to get really big and continue out in this direction right along that line there. And over here, it's going to run along this line right here. Okay, and we'll see some of these. Okay, any questions there? Okay, so the first thing you ask yourselves is this proper or is this improper? Okay, all right. Now, this textbook doesn't cover something called a hole in the graph. Okay, you will see that in your Math 1050 class, so I would like to cover that here. So you won't see any in the assignment like this. You'll only see the examples that I do in class that have holes in the graph. Okay. So after we find the horizontal or the oblique asymptotes, the next thing we want to do is we want to find the vertical asymptote and any holes in the graph. So a hole is exactly what it sounds like. It's just a point in the graph that happens to be missing, okay? So if I had a line that looks like this and I had a little hole right there, that's it, okay? That's what we're talking about. I mean, the name says it all. It's just a little hole in the graph, okay? So we usually find vertical asymptotes and holes in the graph by first finding the zeros of the denominator. So we're going to find the zeros of the denominator. So the way we're going to do this is we're going to factor the numerator in the denominator, and we're going to find the numbers that make the denominator equal to 0. Because remember, we can't have the denominator equaling 0. Okay, those numbers would not be in the domain. Okay. Now, this is just buried in this paragraph, but take a look at this. A number that makes the denominator equal to 0 is not in the domain. If the factor that produced that denominator cancels, there is a hole in the graph at that x value. Okay? So if that value, or that factor that produces that 0 cancels, then it's a hole. If it doesn't cancel, then we've got a vertical asymptote at that x value. And I'm going to show you how that works. So same type of problems right here as we had above. In fact, I think some of these are exact repeats. Here's what we do here. If you want to find the domain, you want to figure out where the denominator equals 0. So in order to do that, make sure the numerator is factored. It is. And make sure the denominator is factored. Is the denominator factored? X squared minus 1. Nope, that is a difference of squares. So that's going to be x minus 1 and x plus 1. Now, I can't have the denominator equaling 0, and that will happen when x is equal to 1 and when x is equal to negative 1. Correct? Okay. Now, here's how you tell whether or not it's a hole or a vertical asymptote. Okay. Does anything cancel here? Could we simplify this? I can cancel this with that. Okay. That makes the 0 that came from that factor, that makes this a hole, and that makes this a vertical asymptote. And I'll show you how we deal with those and how we actually graph these in a second. Okay? But it's that simple. This right here is a hole, and this right here is a vertical asymptote. So I've got a vertical asymptote at negative 1, and I've got a hole. I've got no function value at positive 1. Okay, let's take a look at the next one. Again, in order to figure out what the domain issues are, I've got to factor everything. So if you take a look at the numerator and the denominator, this does factor. That's a 4 and that's a 1. And this is the negative 1. Factoring does not go away, and you've got to be pretty quick at it sometimes. The numerator factors and the denominator factors. I'm looking for numbers that multiply to be negative 8 that combine to be positive 2. So that's going to be negative 2 and positive 4. Any questions? What can I not plug in here? Can't plug in a 2. What can I not plug in here? A negative 4. Does anything cancel? Yes, it does. This cancels. Okay, so this would be the simplified version of the rational function. Okay, what does that make x equals negative 4? That makes this a hole, and that makes this a vertical asymptote. Again, if the factor that produces the 0 cancels, it's a hole. If it doesn't cancel, if it sticks around, then it's a vertical asymptote. Any questions? Does this factor multiply to be negative 3 combined to be positive 1? Doesn't factor. Okay? So, what's the 0 from the denominator? Negative 2. Does it cancel? No. So what is it? The vertical asymptote. Okay. Any questions? Okay. We're getting close to being able to produce a graph here. Hopefully we can do one before we leave. Okay. In addition to finding the horizontal asymptote, okay, or oblique asymptote, and you can't have one of both. Okay, you might want to think about why that is. You can't have a horizontal and an oblique asymptote. Okay, and finding the vertical asymptote and where the domain is, and if there are any holes or anything like that. We usually want to graph the intercepts. Okay, for sure. And we want to be aware of like the end behavior or maybe the multiplicity of zeros and stuff like that. So let's talk about how we find the X and Y-intercepts. So if you're going to find the X and Y-intercepts, remember to find the X and Y-intercept, make a little XY table, plug in a 0 for X, that will find you the Y-intercept. And plug in a 0 for Y, set the function equal to 0, and that will find you the X-intercept. Okay? So I've got a little caution right here. Make sure you use the simplified version to find the X-intercepts. Okay, so here's what I mean by that. The easiest thing to find on these is the Y-intercept. So if I plug in a 0, you can just look at this. If I plug in a 0, the numerator is 0 minus 1, that's negative 1 on the top. 0 minus 1 on the bottom, that's negative 1 on the bottom. So what do I get? I get a positive 1. Okay, so there's the Y-intercept. Okay, now, if I want to find the X-intercept, I want to go through that process I went through just a second ago. We want to make sure that everything is factored. We want to cancel this. So here's the simplified version. The simplified version is a 1 on the top and an X plus 1 on the bottom. Now, if I put in a 0 for Y, that's the same as setting this equal to 0. That's the same as setting it equal to 0. What's the only part of a fraction that can make the whole thing equal to 0? What's the only part of a fraction that can make the whole thing equal to 0? Can the denominator make the whole thing equal to 0? No, because if the denominator was 0, it would be undefined, right? So you can really ignore the denominator and you can just say, well, does the top ever equal 0? Does 1 ever equal 0? No. So this doesn't have any X-intercepts. No X-intercepts at all. Huge piece of information. It never touches or crosses the X-axis. There are no points right on the X-axis. Gigantic piece of information there. Let's take a look at this one right here. Again, if we're going to find the Y-intercept, the Y-intercept is very easy. Plug in a 0. You can just look at it at the beginning. If you plug in a 0 here, you get 0. You get 0 here. The top is negative 4. The bottom, 0, 0, negative 8. So what's the Y-intercept? Negative 4 over negative 8, so positive 1/2, right? Now, if I set this equal to 0, don't just blindly go through and set the numerator equal to 0. Remember, I said you need to set the simplified form equal to 0. I've got this factored up here. So the simplified version of this is r of x equals 2x minus 1 over x minus 2. Any questions there? It's a lot easier to work with the simplified version than work with all of these factors right here. And what makes this equal to 0? Only the numerator. And when does 2x minus 1 equal 0? When x is positive 1/2. So that's kind of interesting. The y-intercept is 0, negative 1, or positive 1/2. And the x-intercept is 1/2, 0. Okay? Any questions? Okay. So again, only the numerator can produce the x-intercepts. So here's what I'm hoping we can do. We're going to look at this problem right here. This is a problem off your assignment. It's not the whole problem, but it's part of it. I think it's problems 10 through 16 or something like that. You have some graph matching to do. Some matching. Okay? So let's take a look at this right here, and let's figure out what we know about this. All we've been talking about so far are vertical asymptotes and holes, horizontal and oblique asymptotes, and then about intercepts. Okay, let's talk vertical asymptotes. Does this have a vertical asymptote? Does it have a 0 in the denominator? Is there a number that makes the denominator equal to 0? What is it? Negative 4. Does that factor cancel at all? Nope. So that's a vertical asymptote. Could we find a vertical asymptote at negative 4? Yes, we could, right here. Does that mean B is the answer? Maybe. But we've got a couple of other choices here. Let's check and see. Now, if I notice down here, where does this one have a vertical asymptote? At x equals positive 4. Now, to my eye, that's positive 4 right here. That's not what this one is right here. So could we be pretty darn sure that A goes with this one, or sorry, that B goes with this one right here? We could be pretty darn sure. Here's what we'd want to do just to make sure. Does this have a horizontal asymptote? And the question there is 2 words, proper or improper. What is this? Improper. It's improper because that's degree 1 and that's degree 1. Good type or bad type? Good type, because they're both exactly the same. What's the leading coefficient on the top? 1, and on the bottom? 1. So y equals negative 1 would be a horizontal asymptote. So let's take a look at this. Does that look like a horizontal asymptote of negative 1? Yes, it does. I feel pretty confident that saying the answer to I is B. We'd match up I with B. Where does this one have a vertical asymptote? X equals 5. That would be our vertical asymptote. Here's a vertical asymptote of 5. There's nothing else to choose from, so this one's got to be A. This one right here's got to be A. But let's double check and make sure. Does this have a horizontal asymptote? Yes, it does. Question is this proper or improper? It's proper. So we would have y equals 0 is a horizontal asymptote. And does that look like what we have here? Yeah, so pretty darn confident in II being A. Any questions? Okay, so flip the page over. This looks like an absolute mess. Seriously, you want us to go through 7 steps to graph these? Okay. And the answer to that is yes, but by the time we're done with this and we do a couple of them, it's not going to seem like 7 steps because they just kind of flow one into the other. And some of the questions are pretty darn easy. Okay. The first thing is locate horizontal or slanted asymptotes. So go ahead and spell that. So you've at least done it once. I think I spelled it every other time for you. So it's asymptote, A-S-Y-M-P. Very silent M and P there, asymptote. If it's proper, it's y equals 0. If it's improper, the good type is leading coefficient over leading coefficient. The bad type, you've got to do long division. Okay, the next thing we'd want to do, we'd want to factor the denominator to find the domain, and then factor the numerator and cancel any common factors. We want to make sure we've canceled any common factors so that we're using a simplified version. We want to locate vertical asymptotes and wholes. Okay, remember, vertical asymptotes are zeros in the denominator that do not cancel, and wholes are zeros in the denominator that do cancel. So if they cancel, they're wholes. If they don't cancel, they're vertical asymptotes. We want to find the X and Y-Intercepts, which we do on nearly every function that we graph. Okay, remember, we want to use the simplified form. Oops, simplified. Okay, and only the numerator can make the fraction equal to 0. So when you're finding the X-intercept, you only need to worry about the numerator. Okay, and that's why it's a good idea to have the simplified form. Okay, and then it says draw the asymptotes, wholes, and intercepts on the graph. So we'd actually draw those on the graph and label them. We're going to use an XY table to determine whether the function is above the x-axis or below the x-axis. Okay, and we're going to plot those extra points that we find. Okay, we're going to basically put all that information together to sketch the graph, and this is where we really need to think and use some logic. Think about what each piece of information means and tells you about the graph. What is an X-intercept? That's where it hits the x-axis, right? Okay. What is an asymptote? That's a line that helps us make the shape of the graph. It approaches that, okay, depending on whether it's vertical or horizontal, okay? What does multiplicity mean about an x-intercept? And stuff like that, okay? And then label the important features on the graph. Now, if you do this other stuff right, step number 7 is kind of done for you, okay? You just kind of want to double check things and put the pieces together, okay? Any questions? Okay. Here's what I'd like to do. You've got enough information. You could get started with just a couple of problems on the assignment. Okay. I'm going to, probably before noon, I'm going to record how to do example number 7. If I get that done, I will send you an email, and I would like you to watch that tonight. Okay. So watch example 7 tonight. Come tomorrow, we'll pick up, we'll do the rest of the problems tomorrow. Okay. All right. Have a great day.